Today we're going to go through a couple of examples on graphing trigonometric functions, specifically sine or cosine. I want to draw your attention back to the notes we took yesterday on the steps for successful graphing. The first step is to determine the period and label your graph accordingly. Then you're going to sketch the skeleton or base graph, either sine or cosine. Sketch the amplitude, reflecting if A is negative. And then we'll go up or down with our vertical shift. I also want to remind you when you're looking at the trigonometric functions where to find all of these things. So the amplitude is of course the A value, the period change, which is 2 pi over b. That b value is going to be in front of either x or theta. We may have a theta in some of our examples today. There will be no c value because we are not dealing with a horizontal shift. And then last but not least, your vertical shift is in the back. It'll be added or subtracted to the end of our function. Also keep in mind that the sine function crosses the origin and then it goes up to a hill and then down to a valley, whereas the cosine function starts at the top of the mountain at 0, 1 and then goes down and back up. So this is our first example. We're going to jump in with both feet. First and foremost, I want to make sure we understand where all of these pieces are coming from and what each one of them represents. So the 3 in the front is my amplitude, which means that is the distance from the midline. The 2 is going to help me find my period. Now understand that 2 is not the period. 2 is going to help me find my period. Keep in mind that period equals 2 pi over b. And then last but not least, the -1 means the entire function is going down 1 unit. So on steps to successful graphing, the first thing we need to do is identify the period. Well, we know the period comes from 2 pi over b. In this case, my b value is 2. Well, 2 pi divided by 2 means my period is pi. So that means between 0 and pi, I need to have an entire hill valley. Now, typically, in a traditional graph, the cosine function would look like this. What we want to do is we want to squish it so that an entire period happens, a hill valley happens between 0 and pi. So in a lighter color other than red, we'll do a light pink so we can still see it. I need for an entire hill all the way down to another top of a hill to happen between 0 and pi. Now, if I'm at the top of a hill at 0 and I've gone all the way down and back up to the top of a hill at pi, that means my valley needs to be halfway between 0 and pi. So now I'm going to kind of guesstimate that that is my cycle whose length is 1 period. And because I have all of this room, I'm going to continue this pattern. Having a hill and a valley in between 0 and pi. A hill valley 0 pi units. Now, of course, this is going to keep going and going and going, which tells me that my domain is from negative infinity to positive infinity. That is something that is never going to change no matter what transformations have happened. Your domain is always going to be all real numbers or negative infinity to positive infinity. Things that could change are my range. And things that change my range are the amplitude and then the vertical shift. So next we're going to go into the amplitude. The amplitude is 3. That is the a value in the front of the function. And that changes my distance from the midline. So my distance from the midline is going to be 3 units up. So all of these points need to go up or stretch. My maximums are going up 3 units, and my minimums are actually going down. To -3. Because we need to be 3 units away from the midline. So now my graph is very, very tall. Now the x-intercepts have not changed. So those x-intercepts are actually going to be the same, as close as they can be. Notice the blue line and the pink line have the same x-intercepts. If this was drawn perfectly, they would. Now, the last thing that needs to happen is this entire function needs to move down 1 unit. The entire function. So all of these points that I've just drawn all need to go down 1 unit, because the midline is also going to go down 1 unit. So now I'm going to draw my new midline in purple. And I have to keep these hill valleys pretty consistent. So I'm just going to draw where my intercepts should be. They're all moving down 1 unit also, to try and help make this as accurate as possible. It's pretty satisfying drawing these graphs up and down. One thing when we're drawing these graphs, I would like to remind you that these are cyclic graphs. They move with a ebb and flow. It's not like a absolute value function where I go up and then go down. So sometimes people will refer to trig functions as hills and valleys, and I think you've heard me say that before. So we're going up to a hill and down to a valley. There is nothing sharp about these trig graphs. So we don't want to do that. We want to make them nice hills and valleys. Now that we've gotten my graph finalized, looking at the purple, we want to identify my range. I know this is very messy, and for some of my friends it's kind of hard to focus. It was really hard for me to focus for the longest time, but I want to identify my minimum and my maximum so that I can understand that this range is now from 2 and goes down to -4. The purple graph is my final graph, and we are going from -4 all the way up to 2, with both of those values being included. Now, I would like to pause for a moment and remind you, we are going through all of these steps to show you how to graph these functions by hand and to identify the different effects each piece has. But let's be honest, Desmos.com is a wonderful resource, and you are more than welcome to use it. So, let's do that now. as you can see, I took the equation we were graphing earlier and plugged it into Desmos. And here we have a beautifully drawn graph that is very easy to identify my minimums and my maximums. I would also like to remind you that we can change it to degrees or radians by going over to our little wrench, clicking on radians, making my steps go from pi over 2, and then I can change my axes to negative 2 pi, positive 2 pi, and remember I'm just typing the letters pi. And then my y-axis can go from negative 5 to positive 5, and that gives me a very nice looking graph. Here's a maximum, go all the way down to another maximum. There's a hill valley, that's one period. A hill and a valley has the period of pi units. We can also identify the midline. If I know that my maximum is at 2 and my minimum is at 4, that means the middle of this has got to be somewhere around there. The difference, of course, between negative 4 and 2 would be negative 1. And then to find the amplitude would be the distance from the maximum to the height, which is 3 units. So that would be my amplitude. In our next example, I've decided to utilize Desmos because it is a lot neater of a presentation than what I was drawing. So here's our another example, y equals 4 cosine pi x plus 2. So my amplitude would be 4. The period would be found using the pi value, which is my b, and then we're going to go up 2. So amplitude is 4. My period, remember, equals 2 pi over b, which in this case is that pi. So my period is 2 units, which means if I were to graph this function, since it's cosine, it's going to start up, go down. My hill to hill is going to be from 0 to 2 units. I did mention yesterday that not all graphs are measured in either degrees or radians. Sometimes they are with whole numbers. In fact, with real-world problems, we're going to see time used a lot with these kind of functions. Last but not least, we will have a vertical shift of up 2 units. So we're going to go through each one of these steps using Desmos. First, of course, we start with our basic cosine function. And then we change the period using finding that the period is 2, which means a hill-valley rotation from the top to the top happens between 0 and 2. Now, I also changed the labels for my graph back to whole numbers because it's a lot easier to graph in whole numbers on the x-axis than it is to try and find 2 units between 3 pi over 2 and 2 pi. Next, we take the amplitude into account, which is 4. So my graph is going to have a maximum at positive 4 and a minimum at negative 4. My midline is going to be the x-axis. But then once we take that plus 2 into account, the entire function moves up 2 units. So now my range is from -2 to +6. Sometimes it's fun to just look at all of it in one. So we started with the red function, and the period changed to the blue function. So you see my graph kind of squeezed in on itself. It didn't take as long to complete one rotation, one cycle, one period. And then in the green function, my amplitude came into effect, and then the final purple function is where we moved it up 2 units. I'd like for you to try this next problem on your own. Y equals 3 sine of 4x minus 1. I would like to point out one more time that the period is found when you take 2 pi and divide it by the b value, which is 4. So in this case, your period is 1/2 pi, or pi over 2. Now, because there is a pi in your answer, that is a pretty good indicator that we want to use radians with our labeling of the x-axis. So, you are welcome to draw it by hand. You can use Desmos first, but I would like you to make sure you understand where each of these pieces are coming from. All right, at this time, you should have paused the video, maybe created a graph that looks like this. Oh, snap. Just to remind you, this graph came from a parent function of sine. We found that my period was pi over 2, so that means between 0 and pi over 2, an entire hill valley has come into play. Because this is sine, we start at the origin and we go up to the maximum x-intercept, down to the minimum, and then back to an x-intercept. Once we've got our period defined, you can throw that amplitude in there and then shift it down 1. This last problem I want you to try on your own. I'm not even going to show you an answer. I'm just going to give you a blank graph and say, go to it. You got this, friend. Now, in the Math Excel that I have opened for you, there are practice problems that bring back some of the trigonometric functions or trigonometric material, that we learned back in Math 2, where we had to solve for angles and side lengths using inverse trigonometry or setting up a ratio. So for example, in this triangle, the directions are solve for x. Well, there's my x. This x is, I have a known angle, I have a opposite side, and an adjacent side, which means I can set up a trigonometric equation because this is a right triangle. Thinking back to my trig, what uses opposite and adjacent? So, ka, ha, ha. TOA, that's right, tangent. So I'd set it up, tangent of 35 degrees equals 35 over x. Now to get x out of the denominator, I have to multiply the entire function by x. Oh, x kind of fell off the side there. So now I have x tangent 35 equals 35. Ironic that these numbers are the same. And then I need to solve for x by getting it by itself and dividing the tangent of 35 degrees on both sides. So x equals 35 divided by tangent of 35 degrees. Just as a reminder, you can put this in Desmos. I know not everybody has a graphing calculator at their house with the sine, cosine, and tangent buttons, but you can use Desmos. So just as a reminder, let's go through that here. All right, so 35 divided by tangent of 35 degrees. Now we want to make sure that we're talking about 35 degrees here. So we're going to go back to the little wrench. Oh, sure enough, it's in radian mode. We need to change it to degree mode, and that will change my answer. So the x value, depending on what your answer is asking you to round to, is approximately 49.99 if we're rounding to the nearest hundredth. I have no idea what Math Excel is going to ask you to do, so make sure you read your blue. The other kind of questions Math Excel has for you are questions like this, where it asks you to find the remaining sides and angles. You're going to see something like this, and the directions may be solve a triangle. Well, if you're looking to solve a triangle, that means you need to find all possible sides and angles. So there are 3 sides and 3 angles to every triangle. First, we'll start by creating our right triangle and labeling it accordingly. Now, of course, you can draw your right triangle however you want, but it does need to be a right triangle, and it indicates that C is the right angle. Little b is 80, little c is 82. And of course, I know those are side lengths because angles are capitals and side lengths are lowercase. I will find my third side by using Pythagorean theorem. A squared plus b squared equals c squared. So that means a squared plus 80 squared equals 82 squared. Put all that in your calculator and find that A equals 18. Then we can use our inverse trig to find our angles, B and A. Typically, we would not want to use a rounded value. We would want to use values that were given to us. So to solve for angle A, I want to use 80 and 82. In relation to angle A, 80 is the adjacent side and 82 is the hypotenuse. So I would want to use cosine of A equals 80 over 82. In a previous video, you were reminded that to separate cosine from an angle, we use the inverse. So A equals cosine inverse of 80 over 82. Making sure that our calculator or Desmos is in degree mode before we find this calculation, we'll see that angle A is approximately 12.68 degrees. Now that makes sense because angle A, even though this drawing is not to scale, angle A is across from a very short side. It's only 18 units as it compares to the 80 units of the other side. So it makes sense that angle A would be a very small angle. Now to find angle B, I'm going to change colors so we can differentiate a little bit. I still want to use the known values that I was given at the beginning of the problem. Even though 18 is not a rounded value, if you get a rounded value, I don't want you to use it because it will further throw off the rest of your problem. So for angle B, we're going to use sine because 80 is now the opposite of angle B, and 82 is the hypotenuse. So to get B by itself, we use sine inverse of 80 over 82, which means B equals 77.32 degrees. Now, if you notice, angle A and angle B should pretty much add up to 90 degrees. Now, obviously, we're doing a little rounding in the middle of this problem, so it may not be exactly 90 degrees. But if I do say so myself, angle A and angle B seem to add up to 90 degrees. If you will, please go practice graphing and refreshing yourselves on our right triangle trigonometry in the Math Excel titled Trigonometric Graphs. And folks, I hope you have a wonderful day.